On the 3rd of October, an object called 3I/Atlas will make a close approach to Mars. At its nearest, it is expected to come within about 29 million kilometers of the planet. For context, that may sound like a large gap, but in astronomical terms, it is uncomfortably close, especially when we consider that Mars has several orbiters in position, such as NASA's long-serving Mars Reconnaissance Orbiter. Instruments on these spacecraft are capable of observing the comet in great detail, but they may also be vulnerable if the object comes closer than expected. Most space warnings over the years have been aimed at Earth, with scientists tracking asteroids and comets that might threaten our own planet. This time, the attention has shifted. The current concern is focused on Mars. Recent orbital models suggest that 3I/Atlas, an interstellar comet, is passing through the solar system on a trajectory that places it dangerously near the red planet. The story of how this warning emerged begins with routine work at Harvard's Center for Astrophysics. Researchers there had been following 3I/Atlas for months, expecting it to pass Mars at a safe distance. But in the early hours of the morning, shortly after 2 a.m., their updated orbital models showed something different. What had previously looked like a harmless flyby was now recalculated as a much closer approach, one that appeared to take the comet inside the orbit of Phobos, Mars's innermost moon. That's less than 6,500 kilometers above the Martian surface, a range that is tiny compared with the millions of kilometers usually involved in planetary flybys. At first, the change was treated with caution. Models are updated regularly, and small adjustments in the data can sometimes shift trajectories in unexpected ways. But the reduction in the margin of error was dramatic. Instead of a wide range of possible paths, the new simulations suggested that the comet's track might be far narrower, with Mars suddenly much more at risk. It wasn't a confirmed collision course, but the probability of impact had risen significantly, enough to warrant serious attention. Within hours, the atmosphere inside the research facility shifted. Graduate students and postdoctoral researchers reran simulations on high-performance computers. Data was pulled from large observatories such as the James Webb Space Telescope and the Very Large Telescope in Chile. With every update, the trajectory seemed to edge a little closer to Mars. By midday, internal communications marked the situation as urgent. A press release was drafted, though not yet released, and messages circulated across scientific teams. The growing concern was not that a collision was certain, but that the risk profile had changed. Even a low probability of impact is meaningful when the potential consequences involve a whole planet and the spacecraft orbiting it. For scientists, this was reason enough to flag a warning. As the news reached NASA, the Jet Propulsion Laboratory, which specializes in orbital dynamics and planetary defense, took over much of the analysis. Their analysts began running updated simulations, drawing on telescope data from across the world and from orbital assets. Their findings confirmed the Harvard team's assessment: 3I/Atlas was on a trajectory that could bring it much closer to Mars than initially thought. The projected distance was still in the range of over 1 million miles, or roughly 1.2 million to be precise. But that figure was within what NASA defines as a monitoring zone for high-risk flybys. The comet is traveling at around 54 kilometers per second, and the path it is taking is unusual. It is approaching on a retrograde orbit, moving against the general direction in which most planets and objects in our solar system travel. This geometry increases the relative speed of the encounter, and therefore the potential energy of any impact. Even if the object only passes near Mars without colliding, its speed and angle raise the chances of unpredictable events, such as debris shedding or sudden shifts in trajectory caused by outgassing. To manage this uncertainty, JPL engineers turned to what are known as Monte Carlo simulations. These models take the latest observed data and generate thousands of possible future paths. The results are usually displayed in what is called a fan diagram, a spread of lines representing different potential trajectories. Most of these lines showed 3I/Atlas missing Mars by a safe distance. But a small number of outliers passed uncomfortably close, in some cases inside the orbit of Mars's outer moon, Deimos. That was enough to classify the situation as requiring active monitoring. At this point, NASA's internal systems triggered automatic alerts, the same ones usually used for Earth-threatening asteroids and comets. This was the first time the system had been activated for a potential encounter with Mars, rather than our own planet. From then on, the event was treated not just as a theoretical scenario, but as an operational concern. Mars orbiters were told to adjust their observation schedules, radar networks were pointed toward the comet's approach corridor, and planetary defense teams extended their focus to include another world. The reasons for this level of caution became clearer as astronomers studied the comet's behavior in more detail. Observatories noticed something that did not fit the typical pattern of comet activity. Time-lapse images revealed a repeating signal, not in radio frequencies, but in bursts of gas from the surface of the comet. Every 17 minutes, almost like clockwork, 3I/Atlas released a jet of gas and dust. This was highly unusual. Normally, comets erupt in irregular, uneven bursts as sunlight heats their surfaces and triggers outgassing. The process is messy, depending on surface cracks, composition, and solar heating. But in this case, the bursts were consistent, timed almost like a metronome. The strength of each jet was similar, and the direction shifted slightly as the comet moved. In practical terms, each burst acted like a small thruster, nudging the comet gently along its path. The changes were too subtle to notice with the naked eye, but over long distances they could alter the trajectory in significant ways. Astronomers explained the effect with an analogy. If a baseball is nudged by just an inch every few meters, it might end up missing the glove by a large distance by the time it reaches the catcher. The chemical composition of the bursts was consistent with known cometary materials, such as cyanogen and carbon monoxide. But the regular timing was unprecedented. No previously observed comet had released material in such a predictable rhythm. This strange behavior complicated orbital calculations. Normally, models assume random outbursts that add uncertainty but not in a patterned way. Here, the outbursts were predictable but continuous, forcing analysts to update models repeatedly. The implication was that the comet might be able to change its path in a semi-regular fashion, creating more uncertainty about exactly where it would be at the time of closest approach. Even if most simulations showed a safe flyby, the rhythmic gas jets left open the possibility of small but cumulative shifts that could alter the outcome. The truth is more complicated. Mars is not a protective barrier for Earth. If 3I/Atlas were to strike Mars, the energy released would be immense, but it would not absorb the impact in a way that shields our planet. At the comet's estimated speed of around 54 kilometers per second, even a glancing blow would release energy many times greater than the largest explosions ever recorded on Earth. The blast would send debris high into the Martian sky, and in many cases beyond its thin atmosphere. Some of that debris would fall back down, but some could escape entirely, dispersing into the solar system. The chance of fragments traveling all the way to Earth is low, but it is not zero. Even small pieces of rock and dust moving at high velocity can present risks to spacecraft and satellites if they cross our orbit years or decades later. There is also the secondary effect of what scientists call the halo. When an object of this scale impacts a planet, it does not just leave a crater, it ejects huge amounts of fine dust into space. On Mars, with its weak atmosphere and limited weather systems, that dust could remain in orbit or drift into interplanetary space for long periods. While the probability of it reaching Earth remains small, its impact on Mars itself would be profound. This brings us to what would actually happen if 3I/Atlas struck the Martian surface. The impact energy has been estimated at around 2 million megatons of TNT, far beyond anything produced by human activity. The crater would measure over 50 kilometers across and several kilometers deep, gouging a hole into the Martian crust that would be visible from space. This would not be a small scar, but a major geological feature, the largest fresh crater ever observed on Mars in the modern era. The consequences for human technology around Mars would be immediate. Orbiters such as NASA's MAVEN or the European Space Agency's Trace Gas Orbiter could be hit directly by debris or disabled by the intense radiation and dust cloud. Landers and rovers on the ground, including Perseverance and Curiosity, might not be struck directly, but could suffer from falling ejecta or heavy dust blanketing their solar panels. Even nuclear-powered rovers depend on communication relays provided by orbiters. If those orbiters are lost, contact with ground-based missions could be severely disrupted. The Martian environment itself would change in the aftermath. Dust clouds rising into the thin atmosphere could spread globally, blocking sunlight and causing temperatures to drop sharply. Mars is already cold, but the effect could push it into an even deeper freeze, a kind of artificial winter that might last for years. Solar-powered equipment would find it difficult to generate electricity in the reduced light, while temperatures could drop low enough to affect mechanical systems. Another effect could be the loss of atmospheric gases. Large impacts can accelerate atmospheric escape, especially on planets with thin atmospheres like Mars. Over time, this might deplete what little atmosphere Mars already has. At the same time, ice locked underground could vaporize when exposed by the blast. Some of this water vapor could linger, but a significant portion would likely escape into space as well. The impact could also create a temporary debris ring around Mars. The material launched into orbit by the explosion would eventually fall back down, but for a time it would pose a hazard to spacecraft. Orbiters could be struck by fragments, and future mission planning would become much more complex. Beyond the immediate risks, there are longer-term implications for exploration. Mars has been the focus of decades of research and investment. Billions of dollars and years of effort have gone into sending spacecraft, landers, and rovers to study its surface and atmosphere. If a large-scale impact destroyed or disabled much of this equipment, it would set back research significantly. Plans for future human missions would also be affected. Engineers design habitats, power systems, and life support with certain assumptions about the Martian climate and surface conditions. An impact of this magnitude could rewrite those assumptions overnight. The loss would not only be financial, but scientific. Rovers like Perseverance are currently searching for signs of past microbial life in Martian rocks and soil. Instruments designed for this delicate work could be buried, broken, or rendered useless by widespread disruption. Years of carefully gathered data could be lost in an instant. The possibility of such a catastrophic event naturally brings to mind historical precedents. In 1994, the comet Shoemaker-Levy 9 collided with Jupiter after breaking into multiple fragments. The explosions in Jupiter's atmosphere were so large that they left visible scars bigger than Earth itself, visible to telescopes worldwide. That event was a wake-up call. It demonstrated that major collisions do happen in our solar system, and they can occur without warning. In the years that followed, governments invested in survey telescopes, orbit prediction models, and even experimental missions designed to deflect dangerous asteroids. But all of that work has been directed toward protecting Earth. There is no equivalent system in place for Mars. No international framework exists for how to respond if a comet threatens another planet. There is no coordinated protocol for protecting the expensive robotic missions we have placed there. What 3I/Atlas highlights is a blind spot in planetary defense. We have assumed the next threat would be directed at us, not at our neighbor. This raises a new question. How should the international community handle risks to planets other than Earth? Agencies such as NASA and the European Space Agency are now discussing whether monitoring and defense strategies need to expand to include Mars, and perhaps even other bodies where humans have assets or future ambitions. Private companies like SpaceX, which plans to send people to Mars in the coming decades, are also paying close attention. The concern is not just about protecting equipment, but about ensuring that future missions have a stable and predictable environment to work within. The challenge is that we may not have time to build such a system before 3I/Atlas makes its closest pass. While most models suggest the comet will miss Mars, a small number of trajectories still point to a dangerously close approach. This uncertainty will only shrink as more data is gathered, but it cannot be eliminated entirely until the comet has passed. The problem is not just distance, but behavior. The repeating bursts of gas every 17 minutes act like tiny engines, changing the path in ways that are hard to model in advance. This makes prediction more complicated than usual, even with modern computing power. As the countdown continues, the world's telescopes and observatories remain focused on the comet. Every new observation is used to refine the models, narrowing the spread of possible paths shown in the fan diagrams. The majority still show a near miss, but a handful continue to suggest a much closer encounter. Until those lines are removed completely, the sense of caution will remain. What makes this situation unusual is the level of global attention. Normally, the risk of impact is discussed quietly among scientists until more certainty is reached. This time, the possibility of a strike on Mars has captured public imagination. People are watching not because Earth is under threat, but because another world that we have explored so thoroughly is in the spotlight. The potential loss of decades of effort and progress makes the story matter in a very real way, even if humanity itself is not directly endangered. The broader lesson may be that planetary defense cannot stop at Earth. Our machines, our research, and our future ambitions extend to other worlds, and they too may face risks from the cosmos. Whether or not 3I/Atlas strikes Mars, the discussion it has sparked will likely continue. It reminds us that space is dynamic and unpredictable, and that readiness means thinking beyond our own planet.